All right, I will begin. Heavenly Father, we thank you again for this opportunity we have just to meet together and to study your creation. I just pray you to guide our thoughts today, Lord. In your name I pray. Amen. Okay, so we proved with some care the isomorphism theorem last time, right? So, theorem, first isomorphism theorem. And simply states this: if we have alpha going from a group G to a group H, a homomorphism of groups, then G mod the kernel of alpha is isomorphic to the image of G under alpha. So, a special case if alpha of G equals to H, then we get that G mod the kernel of alpha is isomorphic to H itself, right? So for a surjective homomorphism, this gives us that the domain mod the kernel is actually isomorphic to the codomain, the image, the range, whatever you want to call it. So let's look at some examples of this. So example 6 of section 2.10. Here, we're going to argue that if G is cyclic, then it must be the case that G is isomorphic to the integers, or G is isomorphic to Z mod n, the modular integers, if you like. So the proof, these examples are often like little propositions or theorems in disguise, aren't they? They're not really examples. I think he just wants to be nice. It's like, students will feel better if I call certain theorems examples, right? So it's like, yeah, this section has more examples, there's less theorems. It's good. But this is really a theorem, isn't it? I mean, honestly, proof. That's fine. If G is cyclic, that means we can write it as being generated by some generator A, right? And then define alpha of k, right, equals to a to the power k. So this makes what? K an integer, right? So notice alpha is a function from the integers to where? To G, right? And is it surjection? Is it onto? Right. By definition of cyclic, this is a surjection. Right? Is it a homomorphism? If we take alpha of k plus j, what do you got? A to the k plus j. By laws of exponents, we never actually proved, but I sketched the proof of, because the actual proof of them is much suffering. We just don't have enough time. Life is short. You don't want to prove laws of exponents. Let's see here. So alpha of k, too late for me. I already did it myself, but I can't get back those 3 days. I don't know, maybe you like that sort of thing. I don't know. This is how some people feel about other people who have children, right? But, I don't personally feel that way, but I understand there are those who do. Anyway, there you go. So it's a homomorphism. It's onto. And so by the first isomorphism theorem, the integers mod the kernel of alpha, right? Z mod kernel of alpha is isomorphic to what? It's isomorphic to G, right? But what's the kernel of alpha? it's k such that what? Such that a to the k is equal to 1, right? So there are two cases, right? Either A has infinite order or it has finite order. If the order of A is equal to infinity, then kernel of alpha is just the set containing 0. If the order of A is equal to n, then the kernel of alpha is nothing more than nz. So you either get that the integers mod 0 is isomorphic to G, right? Or you get the integers mod nz is isomorphic to G. The first case being z itself, and the second case being zn up to isomorphism. Any questions? All right. Example 7. Here we have K, a normal subgroup of G, and K1, a normal subgroup of G1. All right. We want to show that the Cartesian product of K and K1 is, in fact, a normal subgroup of the Cartesian product of G with G1. And to boot, we want to show that the quotient of the Cartesian product of G1 and G1 to K and K1 is isomorphic to G mod K cross G1 mod K1. Okay, so without the first isomorphism theorem, I mean, I think you could do it. You can construct the maps and show that they're isomorphisms, right? But the first isomorphism theorem just makes life so much easier. So basically, we just need to come up with the appropriate map. So can you guys guess what that map should be? I want alpha. I want to go, alpha goes from G cross G1 to, let's say, G mod K cross G1 mod K1. What should my map be? Alpha of, let's say, x comma y. I'll start you out. It's got to be K something, K1 something, right? I mean, you got to define it to be some kind of coset. X and y, because why not? Yeah. That would at least make sense because, you know, x is an element of G and y is an element of G1, so those are defined right cosets. So that map is well defined. I mean, we're not defining, the cosets are in the range, not in the domain, so we're well defined is okay. It's definitely into. That formula is an element of, you know, this is clearly an element of this, right? So what do we need to check on then? We should probably make sure that this is in fact a homomorphism, right? Let's check that. How does that look like? So x, y, x prime, y prime, let's say. That's alpha of x, x prime, y, y prime, where the products in the first and the second components there are taking place in G and G1 respectively, right? And then that's equal to k x, x prime, k1, y, y prime, which by the definition, and this makes sense because we're given that k1 and k are normal, right? So the coset multiplication is well defined in the factor group. Just invented an extra comma there, ignore that. And then you just, what is that? Well, that's kx, k1y times kx prime, k1y prime. See, both the domain and the codomain are product groups. How do you multiply things in the product? Component-wise, right? So I'm using the input here, I'm using the fact that the domain product, right? this last step, I used the fact that I'm working in the product group, G mod K cross G1 mod K1, right? And we know that's a group. Anyway, there what you got. So there it is. That's alpha of xy, alpha of x prime y prime. As you can see, alpha is a homomorphism. All right. Is it onto? Here, I'll pick a point in the codomain. Pick a point in the codomain. How about kx, ky? Yeah, k1y. But yeah, that's an element of the codomain. And can you guys tell me, this is really hard, what maps to that? Yeah. Okay, so it's almost embarrassing to write this down. Like this is a good example of a map where you could say alpha is clearly a surjection, right? It is something you should write if you're going to use it logically, but I wouldn't be super upset with you if you didn't prove it here, because I do think it's clear. Anyway, so moreover, the kernel of alpha, what's that? This would be xy in G cross G1 such that what? Alpha of xy is equal to 1 over here, right? Let me just write what is 1? Right, it's k, yeah, k1, right? So what is, let's just pick on this. What's this mean? This means that kx, k1y, right, has to be an element of k cross k1. Or more to the point, we need kx equals to k, and we need k1y equals to k1, right? So what is the kernel? What's this mean? So x is in, yeah, x in k, y is in k1. So in other words, this is nothing more than k cross k1. And the example follows. I'm sorry, theorem. I'm sorry, example, whatever this is. So the domain mod the kernel, which is k cross k1, is isomorphic to the range, which is g cross g over k mod, g over k cross g1 over k1 by the first isomorphism theorem. Right. This is very nice because you notice we don't actually have to check the normality of the thing that we're quotienting by. We know it's normal because kernels are normal, right? I mean, there's a lot of labor saving that's going on here by using this theorem. Example 8. I'll try to be a little bit quicker with this one. Here we have the claim that R mod the integers is isomorphic to the circle group, C0, which we'll write as e to the I theta, such that theta is a real parameter. So basically here, just look at alpha, define alpha from the reals to C0 by alpha of x equal e to the 2 pi I x. You can easily check that that's a homomorphism by the usual properties of the complex exponential. And its kernel, what's its kernel? So that would be x in the reals such that e to the 2 pi I x equals to 1. If you want me to unwrap this, what this means, this is the same as saying that cosine of 2 pi x equals to 1 and the sine of 2 pi x equals to 0. What's the common solution to those two real equations? Yeah, any integer. So So that says that the kernel of this map is the integers. Consequently, R mod the integers is isomorphic to C0 because that mapping is onto. Every unimodular number has the form e to the I theta for some theta. You can pick x to be what? If I want to map to I theta, what do I pick x? What's that? 1. Now I want alpha of x to equal to e to the I theta. What do I make x equal to? What's that? There's the proof of onto. Okay. Given our presentation of C0. Yeah. Of course, this theorem has other uses. It also has use for, say, figuring out what are possible homomorphisms and things like that because of various ways structure is preserved. This is example 9, which studies the interplay between normal subgroups and homomorphisms because they're interrelated, you know, in the following sense. How are homomorphisms and normal subgroups related? If you're claiming that a subgroup is the kernel of a homomorphism, what has to be true about that subgroup? Yeah, it has to be a normal subgroup, right? Not all subgroups are normal, which means not every subgroup can be made the kernel of a homomorphism, right? So we want to look at D3 and also the cyclic group of order 6. We'll use C as the generator. The goal of this example is to find the homomorphisms from D3 to C6. Find all homomorphisms from D3 to C6. So what are the rules? What are the rules to this game? What's that? Right, we have to, every homomorphism has a kernel, right? So we can't like find homomorphisms without kernels. We're stuck with a kernel. Every homomorphism's got a kernel. And those kernels can only be the normal subgroups of D3, right? So what are the normal subgroups of D3? Yeah, 1. Yeah, D3 itself. Is there anything else? Right. The cyclic subgroup, this guy, right? Yeah. Because that has index 2. So we can always just ignore the reflection part of the dihedral group and just keep the rotation piece, and that'll be normal. That's always there. Yeah. B, BA squared. Geometrically, these are all reflections. The 1, the A squared, these are rotations. Anyway, so them's your choices. Either got 1, so here are the choices. 1, we can have the kernel of alpha equal to 1, right? 2, we can have the kernel of alpha equal to all of D3, right? So how do you get kernel of alpha equal to 1? You say alpha of x equals to what? 1 for all x in D3, right? This is a homomorphism.
Isn't that for 2?
Oh, I'm sorry. You're right. There we go. Sorry about that. So if I do that, then I get the whole thing being the kernel, right? So how can I make the kernel just one? But that doesn't make sense. Because X is in D3, whereas the image should be in, I mean, this is the one, these are not the same ones, actually, technically speaking. This is one in D3, this is one in C6, I mean. What's that?
There's no homomorphism. There's C6 cyclic, but D3 is not. I mean, if you take the map between.
So let's flesh out what he's saying. Mr. King has the right idea here. So if we look at D3, right? First isomorphism theorem would say D3 mod the kernel, which we're saying would be 1, hypothetically. Then by first isomorphism theorem, that would be isomorphic to what? C6. How do I know it has to be C6? It's injective. It's a finite map between two things with 6 elements, so it must hit everything, right? So this would say that D3 is isomorphic to C6, which is nonsense because D3 is, like you said, it's not cyclic. It's also, what, not abelian, right? I mean, D3 is S3. We learned that earlier. Seems like that might have had something to do with a test. But anyway, but yes, in fact, this possibility is in fact no can do. All right? There's an earlier example in an earlier section where we're just thinking about sending generators to generators, right? How many generators are there? How many generators are there in D3? I mean, you got A and B, right? What else could you use to generate it? I think you could use what you could use A squared and B. I think could also work. How many generators are over here? Well, I guess I just need to think about one set of generators. A and B are generators here, over here. I'm trying to remember the counting. There's some counting which tells us there should be 6 possible homomorphisms, you know. Just raw counting of generators gave 6 possible homomorphisms in an earlier example. I forgot to bring my book. I'd tell you which one, but anyway. So the third case, but my point is here, that counting is further refined by using the first isomorphism theorem is the point of this discussion, right? Actually, all 6 of those possibilities aren't realized. In fact, there are only 2 homomorphisms. We're about to find the other one, which would be kernel alpha equals to what? This thing, right? And a short calculation shows you that the formula you want to put there is b to the k, a to the m equals c to the 3k. This will define a homomorphism. This will define a homomorphism from D3 to C6, which takes the cyclic subgroup of D3 as its kernel. Yeah. Oh, yes. Goodness gracious. What's wrong with me? So many things, but anyway, that's just one of them. Yes. You can check this formula. First of all, it's a homomorphism, but second of all, if you try plugging in, certainly, if I set this equal to 1, what does it say? If I set this equal to 1, what do we get? K equals to what? Two or 0? All right. So in either case, that means that b to the k am is just equal to a to the m, right? Which is to say that m is free and all possible powers of a are in the kernel, which is exactly what we want. 1a and a squared are in the kernel. Anyway, so there's that one. Where I put my, oh, here it is. Phew, yowzers. It is hot in here today, isn't it? Well, it's hot to me. May not be hot to you guys. But so to apply the first isomorphism theorem, you got to have some kind of insight, like what map should I use to do it, you know? And sometimes that's not obvious. It's Theorem 5. It says that G mod the center of G, all right, it's isomorphic to the inner automorphisms of G. All right. And so you recall the inner automorphisms of G are what? Not just that, but they're, remember they're yeah, they're conjugations, exactly. They're sigma G, right? Such that G is an element of G. And here sigma G means, was our notation was that was Gx, G inverse. Check it out, I put the G inverse on the right side today, woohoo! All right, small victories. But, so we can define theta, right, to be a mapping from G to the, well, he has the automorphisms of G in the book. I think I'm just going to make it map to NG because why not? And this theta, we're going to do is theta of G. Guess what it's going to be? Sigma G, right? Clearly onto, right? That's an arbitrary element of the inner automorphism, so it's clearly it's a surjection. How about, is this an isomorphism? Well, yeah, I mean theta of xy is sigma xy, which we have previously worked out is sigma x, sigma y, right? Which, of course, is theta of x, theta of y, so therefore theta homomorphism. So we have a surjective homomorphism. So next order of business, calculate the kernel. What is it? So we'd be looking at G and G, right? Such that what? Yeah, theta of G, which is, like you said, sigma G, is the identity function on G, yeah. Because that's the identity element there. So let me just pick on this. This would mean that sigma G of x, which is equal to Gx, G inverse, is just equal to x again for all x in G. But that is entirely equivalent to the condition that Gx equals to xg for all x in G, right? So you can see that the kernel is nothing more than the center of G. So by the first isomorphism theorem, that proves it. The messed up thing about these sorts of theorems is I think the abstract ones, the truly abstract ones, are easier. Like this example over here with D3 and C6 to me is harder. There's pesky details, yeah. Example 10. Example 10. Here we have that the inner automorphisms of S3 are isomorphic to S3 itself. And so the inner automorphisms of S3 are isomorphic to the automorphisms of S3. This is pretty much just an application of Theorem 5, right? Because you might recall we've proved that the center of S3, right, is just the identity permutation. So Theorem 5 would tell me that S3 mod the center of S3, right, is isomorphic to the inner automorphisms of S3, right? But this is just the identity, so we have S3 mod the identity group, which is S3 again, up to isomorphism, is isomorphic to the inner automorphisms. So there you go, S3 is isomorphic to its inner automorphisms. And then to see that the automorphism group is isomorphic to S3, the question is, how big is the automorphism group? Let's see here. So here's where those, I got to erase this so I have room to write about it. So here, you might recall S3 is 1 sigma, sigma squared, tau, tau sigma squared, yeah? And so if we want to define an automorphism that goes from S3 to S3, right, then the order of theta of sigma has to be what? And the order of theta of tau has to be what? I'm sorry, I really don't like this little O notation. You'll forgive me if I instead use order. Put things in order. See here, that's better. It's an automorphism. What do automorphisms do? They preserve order, among other things. So this has to be the order of sigma. This has to be the order of tau. How many elements there are there of order? You know, this has order 3, right? This has order 2. So if you think about it, if you start with sigma, you have to send it to, I mean, how many? There are 2 of these, right? There are 3 of these. There's 2 elements of order 3, sigma and sigma squared. There's 3 elements of order 2, tau sigma squared. And so that means if you count, there's at most, what, 6 automorphisms. So you can't have more than, automorphism group has to be at most 6, order 6. So given that, and the fact that the inner automorphisms of S3 are a subgroup of the automorphisms of S3, right? So this is 6 things. I mean, at most 6 things. This generator business doesn't, that just because there are that many choices of mapping, that doesn't mean that every one of those is actually an automorphism. So there's at most 6 automorphisms, but hey, the inner automorphism group's got 6 things in it. So apparently all 6 of those things are there, and since that's a subgroup, it must be that they're equal because that definitely has 6 things in it, and this has at most 6 things in it, and it's a subgroup. So that forces this to have 6 things, and it forces them to be equal. All right. Phew. Everyone can stretch for a minute. I was going to give a quiz today on rewriting the factorial as the gamma function. Is anyone interested? Emily? No? Are you tutoring? Oh, different Emily. Never mind. A Calculus 2 student come to me today and say that their tutor could not help them with this gamma function problem. So it said the tutor's name was Emily. It's like, no, different one. So I thought I'd give you guys a quiz on that, but it has really nothing, little if anything, to do with what we're doing, but it seemed like it'd be fun. Come on, wake up. You can do it. You can do it.
MarleyGenerics.com or call 1-800.
See, we do not got enough commercializing in here already. Don't need more from my computer. All right, so we have now reached chapter 8. And this is actually a very natural next thing to go to. Partly because section 8.1 contains in it, don't you do that to, what are you seriously? Not cool. So section 8.1 is the natural follow-up to where we are, because section 8.1 has in it the second, third, and fourth isomorphism theorems and generalizations of the product group theorems that we saw in section 2.6, I guess it was. So a lot of the counting formulas that we had there for when the intersection of two subgroups were trivial, they're contained in this section for when they're non-trivial. And it's just a collection of interesting and slightly deeper theorems, none of which I will prove, okay? Except for maybe this one. Not that one, but this one. So here's the first thing. If H and K are subgroups of a group, and if you have H is a subset of M, then H times the intersection is the same as the product of H and K intersected with M. This is called the modular law. I need my laser. So you'll forgive me. But this is, he also has a discussion at the start about how the product of any two subsets in a group makes sense. And basically, the notation, we've been using like H times A for the coset. In terms of his construction, you could say H times singleton, like curly bracket A, that would be identified in the same way. And so essentially, he shows at the beginning of this section that this HK thing is just a natural extension of our right coset construction. But I haven't even written that out. But then we get the second isomorphism theorem, which is also called the Diamond Theorem sometimes. The reason it's called the Diamond Theorem, if I can find my eraser. Oh, there it is. So here we have the statement. We've got subgroups H and K of G with K normal in G. Then the product of H and K is a subgroup of G. K is a normal subgroup of the product, and the intersection of H and K is a normal subgroup of H. Furthermore, this is the relation HK mod K is isomorphic to H mod the intersection of H and K. My stupid radio is still making quiet noise. It's bothering me. I thought I muted it, whatever. Let's see here. I'm trying to think what the right picture is for this. Something like, so here's G, right? We've got subgroup H. We've got subgroup K. Let's see here. Oh, I guess HK is up here, isn't it? Because K is a subgroup of HK, and H is a subgroup of HK, right? So I guess G's not even in the diamond. Oh, I shouldn't have erased that. Oh well. You guys know that by now? Let's see here. So, so G is up here, I suppose, in the lattice diagram. Yeah.
So H and K are both sets. Can you point me where I should look for what multiplication of sets is in this context?
Start at section 8.1. Yeah. It is what it sounds like. It's just all possible products. It's like, it is literally HK such that H is in H and K is in K. It's the thing we did in the section 2.6, we have talked about it, but it's okay. Now down here, of course, you have H intersect K is a subgroup, right? So this is the diamond, I think, that's referenced. And so K is a normal subgroup of HK, right? K is a normal subgroup of HK. And what else do we have? H intersect K is a normal subgroup of H, like this here. And if you look at hk over k, it's isomorphic to h over h intersect k. You see those? See that? This over that is that over that. So you can kind of remember this theorem in its relation to this picture, not in your text. The proof, I should have made time for today, but I didn't, so my apologies. But the proof is actually pretty simple for the second. I mean, I've assigned this as homework in previous semesters, maybe like last year. Well, that's my only choice, right? Anyway, the fact that H is a subgroup and that K is normal in G follows essentially from chapter 2 stuff. And then the rest of the argument is just that this mapping alpha, this mapping alpha defined by just the right coset like that is actually a homomorphism, which here's the details. Surprise! Wow, that was really tough, yeah. And then also the question of whether or not that's well defined is a little bit involved. Here's the argument though, because if I take two different representatives of something in the product hk, which by the way is equal to kh because of chapter 2 stuff, so they're equal. So I can follow through that kx is actually equal to alpha of h, but that means that this h, which I can construct for a given x, maps to kx, which shows you that this is a surjection. Anyway, and then the kernel is the points that are in the intersection of h and k. And so first isomorphism theorem proves the second isomorphism theorem, or the Diamond isomorphism theorem. Theorem 2, here's another general, we had in chapter 2, we had the formula that if h intersect k was the identity, then the size of the product h and k was just the product of h and k. I think we needed that they were both normal, right? Or we needed something, but anyway, here it is. So h and k finite subgroups, then the size of the product times the size of the intersection is just the product of the orders of the subgroups. And the proof is not too hard. It's basically based on the identification that if you look at hk, you can look at it as the disjoint union of these sets, where these k's are taken to be the k's which are needed to form representatives for the disjoint cosets of the intersection. Details are in the book, but once you accept that this is a partition, then you can count. There's m of these. So this has m times the order of h, but m is nothing more than the number of disjoint cosets of the intersection, which is, in other words, the index of the intersection in K. N is h intersect K, so it's the index. But remember that the index of the number of cosets in the intersection is the size of K divided by the size of the intersection, which gives me this is equal to that, which is that. Just neat result.
And that works well with the same diamond picture you have there. You just take the diagonals.
Yes. So, right, yeah. This is theorem 3. Here we have that if we take hk mod the intersection, it's like somebody who didn't know anything of what's going on here, right? Could start writing down theorems and be right just because the notation's so good, right? I mean, the product translates into up to isomorphism a Cartesian product, and you got to make sure that, it's just like if you've got, oh, wait a minute, no, I'm wrong. This is probably not what you'd think, right? If you've got 3 times 5 over 7, you wouldn't say that it's 3/7 times 5/7. So what I'm saying is nonsense. Like the naive thing would be to drop one of those sevenths, right? But this is like, it's both places. So it's not, yeah, it's additive. Oh, I should think of this as addition. Ah. So think of the product, yeah. Okay, yeah. So for an additive group, then the analogy makes more sense, yeah. Okay, good. Anyway, the proof, and after you read about the 5th one of these proofs, you get kind of bored because they're all the same. Basically, hey, look, here's a map, woohoo! and the map goes from hk to the thing we're trying to show is isomorphic to this quotiented by something, you take the map alpha of hk is, n is the intersection of h and k, so this is the natural map. You can argue it's well defined. The fact that it's a homomorphism takes about a paragraph, and the fact that its surjection is not hard to see. The kernel works out to be the intersection of h and k, and there's the theorem. In linear algebra, if you took it with me, we talked about the concept of independent subsets, right? So basically, if we have a vector space and we can find subspaces which are pairwise independent, I mean, they have to, if they satisfy certain independence conditions, then we can say that the vector space is isomorphic to the direct sum of those subspaces. And what I'm about to show you is just the corresponding result for groups. So these are called unconnected subgroups, which topologically I question this terminology, but because certainly in the case of vector spaces, quote unquote unconnected subspaces are very much connected in the topological sense, because you can always run paths through 0 to get to the other one, but whatever. I digress. So the following are equivalent for subgroups. The product of everything except for 1 intersected with the one that's not in the list is just 1. And 2, if you have a product of elements from each of the unconnected subgroups equal to 1, then it has to be that each one of those is 1. So this would be King's independence of 0 comment towards the characterization of independent subspaces in linear algebra. The fact that 0 has a unique representation is recast as 1 having a unique representation. All right, this is not quite 321 though, because our groups are non-commutative. Vector addition is commutative, so it's not just straight vector space or anything like that. But there is a list of equivalent conditions: unconnected, normality of each factor, or the fact that you can commute things from different factors is equivalent to normality. And then ultimately, the ultimate result here being that G is isomorphic to the direct product of these, the direct product of these unconnected subgroups, and any group element has a unique representation as a product of things from these factors. So this is a nice way of thinking. This brings us to, you couldn't see it, but this is sometimes called the Lattice Isomorphism Theorem, or sometimes called the fourth isomorphism theorem. It essentially says that there's some correspondence between, so if K is a normal subgroup, right? If H is a subgroup that's a supergroup of K, but a subgroup of G, there's some interplay between these supergroups of a normal subgroup and the corresponding quotients, subgroups of the coset space, the factor group of K. This is what the correspondence theorem says. And I'm not even going to, we can read this, but I think it's better just to look at an example because you can see with a picture what this theorem is actually saying much more powerfully. Example 1. So here's what this theorem actually says. It says you can look at the lattice of subgroups through G, all right? And if you've got a normal subgroup, in this case K, where K is equal to, K, where is K? Curses, where did I put K? Where's that K? K is the generated by a to the 6th, right? So it's got 1 and a to the 6th, right? It's a subgroup of 2 elements. So that's a normal subgroup of this G. And look at this. So this is the total lattice diagram, right? See what happens here? The lattice of the quotient of G by K, just essentially anything that's below K on the diagram just gets squashed out. And you're just left with, what was there? Mod K. That's what the correspondence theorem says, is that you can create lattice diagrams for subgroups of a factor group simply by taking the lattice diagram for the group in total and just systematically ignoring parts of the lattice. And it's the same relationship. So like another K1 is also normal. So everything that's not under, everything that's sort of above K1 survives. Everything that's not, gone. And so you can see that this becomes that, whereas this becomes that. So this is the correspondence theorem says is that there's interplay between the supergroups of a given normal subgroup and the corresponding possible subgroups of the quotient. I will post this for you guys. He also has this example for the octet group, but I will instead, I'm also going to include for you guys this page. This is the fourth, or the lattice isomorphism theorem. This is the statement of it in Dummett and Foote. And he has a couple of examples that have additional notation that's helpful. So rather than trying two pictures, what he does is he superposes the lattice diagram for the quotient on top of the lattice diagram for G. See, so here's the lattice diagram for Q8, the quaternion 8 group. The lattice diagram for Q8 mod the subgroup generated by -1 is the double lines. Or here, this D8 is a group, you know, that's the octet group, I guess. Or maybe it's, well, I'd have to remind myself what it is in Dummett Foote, but his D8 might be our D4. Anyway, this is a normal subgroup, and the correspondence theorem says that you take the whole lattice group for D8 and just look at this piece, and that's the lattice for the quotient of D8 by R squared. So anyway, with that, I will shut up as I'm over time. I'll post this for you guys in course content, so thanks.